I'd like to have a lecture on the theory of acoustics before going into the numerical aspects. These are largely classical ideas, and there are 5 or 6 important ideas in the lecture. They aren't all necessary for the user of numerical acoustics, so some of you might bog down a little bit. Some of the developments are a little bit picky. So I'll try to explain as we go along what the general idea is, and then if you can get the specific ideas in that topic area, that's fine, and if you can't, you might want to just skip ahead to the next part of the lecture. There are 4 figures, for instance, on the way that pressure and density relate in an adiabatic process. And some of you might have had that before. But generally speaking, I'm not going to consider that anyone watching this has had acoustics before. It will help if you've had a little bit on structural dynamics, if you've had a little bit of fluid mechanics. We'll preview the variables that are involved in the process of acoustics. We'll look at the speed of an acoustic disturbance. These are small isentropic disturbances in a fluid. We'll talk about the speed of sound in several different fluids that obey the Barotropic law. And as limiting cases, we'll have the adiabatic process, which is the relevant one for us. There's also an isothermal process that was considered a candidate for a while, but turned out not to be valid. We'll develop our equations of continuity, momentum, and then the wave and Helmholtz equations in 1 dimension, and then we'll extend those to 3 dimensions. I'll compare finite element analysis with boundary elements. One problem in a problem session. Let's preview the problem that we're going to deal with. I want to point out the acoustic variables and some of the philosophy. Generally, you have a room, could be also an exterior region where there is a medium, and the medium is characterized point by point by fluid velocity, pressure, density, and temperature. There's often a source of excitation, shown here as a loudspeaker, that causes waves to move through this medium. There's typically a receiver of this noise, and it might be a human, shown here, or it might be a sensitive structure that's delicate and is perhaps going to fatigue under high intensity acoustic loading. Now, there are really 3 velocity components in 3 dimensions, and there are 3 of these fluid properties. So in effect, there are 6 variables in the problem. We need to come up then with the equivalent of 6 equations to describe these field variables. And I'll discuss those in the next figure. We have 6 field variables, basically, so we need to come up with 6 field equations that tell us something about the way the fluid can move. We're going to do that in order here. First, there's a perfect gas law that holds point by point in the fluid, and most of you will remember this as P equals rho RT. R is the universal gas constant. For some given fluid, then, R is known. You might think of this as eliminating temperature in the field, although it's often written as if you're solving for pressure, but we'll think of it as eliminating temperature as a variable. Secondly, if you can assume something about the process, and one such dominant assumption is the adiabatic assumption, and this has to do with the fact that there's not external heat addition, and that will take the form of P equals K rho gamma. K is a constant of proportionality. This is particularly useful now when you do a perturbation and you see how a change in pressure can be related to a change in density. You can think roughly of this as eliminating density in the problem. Again, although the equation often appears to be solving for pressure. We'll in fact carry that equation along intact, though, and use it with the conservation of mass equation, which is a scalar equation, and the momentum equations, 3 in number, in a 3-dimensional space. So the way that the problem is finally uncoupled in our approach is to take these 5 equations here, solve them in a simultaneous way, and end up with a single equation on pressure perturbations, and that will be called the wave equation for the transient case. And then when you assume harmonic motion, it's called Helmholtz equation. So much of our course will deal with Helmholtz equation from now on. It will be good to show you the way that that equation is derived. We're going to do it in 1 dimension first, and then show how that would generalize into 3 dimensions. Once you've got the field equation, you still need to apply appropriate boundary conditions. There are acoustic problems where there are pressures applied at a certain surface, other problems where velocity might be applied. You have cases where an impedance on some kind of an absorbing boundary is given. And then lastly, if you have a moving absorbing boundary, you might have separately velocity and this acoustic condition. Now those can be joined together, and we'll show how that's done later in the lecture series. One of the most fascinating calculations done in fluid mechanics is to find the speed of propagation of a small pressure disturbance. We'll do that in the form of a 1-dimensional pressure wave traveling through space, and we'll call it an isotropic process, so there's no external heat addition. And it's just a tiny wavelet that is passing through the air. We will give the speed the symbol c, and that will be used pretty much from now on for the speed of sound. We're anticipating to call it that. An interesting thing is that this small disturbance traveling at speed c can be calculated to travel at exactly the square root of dp d rho. And this equation will hold for several cases in fluids, and is certainly a very clean way to calculate the speed of sound. That turns out to be a constant, and turns out not then to depend on the frequency, let's say, of the pressure disturbance. In our case, we don't even need to discuss a frequency. We'll just take a small jump in pressure. Zucrow does a nice mental experiment where you imagine the flow and a pressure disturbance, and you, as an observer, move with the disturbance. So we'll assume that the disturbance originally was going to the left, but we will ride along with it as an observer. We're then going to see this small control volume in a stationary frame for us, and it will appear that the undisturbed area into which that pressure pulse is propagating is on the left, and it will appear that there is a speed of propagation into the wave, which in effect is the actual speed of that pressure pulse. After the fluid seemingly passes through the control volume, it comes out with an increment of density, velocity, and pressure. And our goal is to relate those. As we travel with that pressure pulse, we will assume that the jump here is shown as below. And so this is a very, very small jump, and we know that in acoustics, typical pressure jumps are only 1,000th of an atmosphere or less, so that I've even exaggerated that pressure pulse for the purpose of this picture. Let's now work out Newton's second law for our pressure jump case. Our control volume is shown here, cross-hatched in red. Basically, there has to be a driving force to accelerate the fluid as it crosses through that volume. One way to do this is just in an average way to take the average amount of mass contained within that volume. That would be the average density times the volume that's enclosed, and that's subjected to an acceleration that is the increase in velocity divided by the time increment to move the material through. Now that's the width of the region divided by the velocity, the average velocity. So we're able to come up with rather simple approximations here. Then, with the second law, we put the summation of forces in the x direction equal to that mass times that acceleration. On the force side, you get cancellation of the dominant terms. You get a surviving term, dp times a, which we carry below here. There is a minus sign on it. The mass here times the acceleration here, when multiplied out, have some cancellation. The dx here cancels the one here. The surviving term is going to be first order term rho times area times dv times the speed of sound, and that's shown here. The remaining terms are second order and higher, and I just illustrate those with the velocity increment squared as being of that order. So we neglect those terms, and we're left with the pressure jump as a function of the velocity jump. Speed of sound entering, density entering. So certainly the material properties are here. Okay, then the second law after this one that we need is the continuity equation. This is a steady process. We're going to require that the flow into the left face equal the mass flow out of the right face. And that's simply the incoming density times the speed times the cross-sectional area. On the exit side, you have the perturbed density, the perturbed speed, times the same area. The areas cancel. Again, we have some higher order terms that vanish here, and we're going to cancel the zero order terms, you might call them, the terms on both sides that are rho c. Then you're left with first order terms all coming from this multiplication in here. You're going to get rho dv plus c d rho, and that's shown here. So that becomes our continuity equation, and with those two equations we can solve our problem. It turns out to be a simple matter now to take the continuity and the momentum relations and put them side by side and solve for the speed of sound. On the left you have the jump in pressure related to the jump in velocity from our momentum law, but the jump in velocity is related to the jump in density. So if we just insert this quantity here into the proper location here, as I've done in this equation, and then cancel the densities that are involved, cancel the signs, and you get that dp is c squared d rho. Well, you solve for the c squared and you get dp d rho. This is the speed of a disturbance propagating in an acoustic medium, and it's valid for small disturbances. Once you have this, you then can look at different kinds of flow situations and decide what the speed of sound is in each case. One general class of fluid and fluid processes is called barotropic, and that's where pressure can be determined just as a function of density. Now we know already that in a perfect gas, temperature is lurking in the background, but it can be accounted for as well. If a barotropic fluid obeys this law, pressure is a function of density only, then it isn't too hard to calculate dp d rho. One just needs to find what is that relation. What is the function rho that gives you the pressure? We'll look at two such cases. One is adiabatic, the other is isothermal. In the adiabatic case, the relevant law is given here. This one can be proven with some 3 or 4 pages of figures, and I'll do that later. But for now, I think many of you are comfortable with this equation already. What does it mean? Well, in the p rho plane of, let's say you have air, for instance, and room temperature and pressure conditions at sea level might lie at this point. Then the value of dp d rho, which also is interesting for the sound, but the slope of a path of that process would be the little red line here. And so a vibrational harmonic sound wave would tend to oscillate up and down on this path. And we would calculate the speed of sound accordingly by looking at what the dp d rho is, what the slope of that process is. In principle, although we don't need to think that generally, it would appear that as a process continued, if it were possible to continue as a barotropic process and adiabatically over larger disturbances, then there would be a continuation, and these different trajectories that I'm showing here would be the generalization of such a family of possible behaviors. But we're really only interested locally in what's going on for very small oscillations. Now, the dp d rho then, which is the slope of such a relation, can be calculated directly since we have this exponential form. The derivative of rho to the gamma is gamma rho to the gamma minus 1. Then, to put that in more friendly form, multiply upstairs and downstairs by rho. This rho upstairs cancels the minus 1, and then you're left with the original pressure, K rho to the gamma, which I've put in parentheses here, and so that reverts ultimately to gamma P over rho. So many people remember that the speed of sound in a fluid is a square root of gamma P over rho. That's true for the adiabatic process. That's the one where there's not much heat conduction. In fact, it's a good way to think of it in terms of the conductivity of the medium. If you have a poor heat conducting medium, then you'll get this adiabatic process for acoustic waves. Another way is to replace the P over rho with its perfect gas law equivalent, RT. And in fact, many of my friends in aeronautics think of speed of sound as purely a function of temperature. So, isn't it interesting, as you go through this process, you start out emphasizing density and converting to pressure, and in the final analysis, it's really the temperature that's the, if you want a single parameter to think about, that controls the speed of sound in a medium. So you have to be very careful specifying properties of the medium to give the temperature. The adiabatic formulation for sound propagation is not the only proposed law, though. An older idea was that of Boyle's law, or an isothermal process. This is based more on the idea that as the process takes place, there's very good heat conduction between the hot and the cold parts of the wave, and so that as it travels along and through space, the temperature equalizes quickly, and such that the compressive regions of the wave really don't get any hotter than the surrounding ambient air, nor do the rarefied portions get colder. Boyle's law is that pressure is just proportional to density. Now, you can do a class of problems like that where you have an initial control volume of fluid and then you perhaps expand it but keep it at the same temperature. Now that's going to require heat addition or subtraction as you do this. It's assumed that the walls of the container are perhaps copper, a very good conductor, and that the fluid's a good conductor, and that this will come to a re-equilibrium in terms of what the wall temperature is. So you kind of overwhelm the fluid's own thermal capacity. That means you're going to be moving along lines as shown here, these short segments. And such a process then could move on a radial line from the origin. Now a sound wave, if it were to propagate in this manner then, would again say at sea level temperature, pressure, density conditions might be here, and would tend to move on that straight line. The dp d rho in this case is just P over rho, and again you get the square root of something involving temperature only if you wish. Now there's no gamma in this one, there's no ratio of specific heats. And interestingly, this sound speed is 16% slower than the measured sound speeds in air and water. And that was what led Laplace to propose that the acoustic waves were really adiabatic rather than isothermal. When I first heard about the paradox of whether sound would travel adiabatically or isothermally, I believe that I was told, and it has been erroneously put in books, that that is due to the fact that the sound wave oscillates rapidly in time, and there's not time enough for the fluid to come to the uniform temperature that the isothermal assumption would have. That's dead wrong. So I note that here. In fact, it's really a question of distance rather than time. Sound propagation in air, say, and water as well, is adiabatic because the wavelengths for our audible frequencies are so long that the heat can't travel the distance required to equalize the temperature. And this means that, in fact, in terms of time, because high frequency oscillations have short wavelengths, it turns out that they are less adiabatic. So the argument was exactly backwards as it was originally presented, that there wasn't enough time for heat to transfer, when in fact the real question is how long are the wavelengths and can the heat travel quickly enough to equalize temperatures. Most air and water situations are at frequencies such that the adiabatic assumption does hold. You have to go to quite a high frequency before you get into the isothermal type of condition. I've tried to convince you that the adiabatic process is the proper one for acoustic waves traveling in air and water over quite a broad frequency range that we're interested in, both for human response and for fatigue of structures and physical bodies like that. Let's look at the proof of the adiabatic law relating pressure and density. It's not too hard to do. It takes 4 figures. It's a little bit tedious. If some of you would like to just jump through these next 4 figures and go on, that's fine. I like to follow the discussion by Pierce in his book Acoustics. The way that this is done is to consider a quantity of gas, let's say in box A, then you add heat but hold the volume of the box constant. So that means that you maintain the same density, but that you get a change in pressure and in temperature. As a second step, and these are meant to be small increments, you add a second small increment of heat, but this time you hold pressure constant. You might, for instance, have to increase the size of that box containing those same molecules of gas, because otherwise you may end up with a higher pressure. But we're not going to allow that. We're going to move the walls holding pressure constant. That leaves the same pressure as we had at stage B, but at this time we allow density to change because the same number of molecules of the gas have now had to expand and fill a larger box. The temperature will change a second time, and indeed there's a temperature jump in both cases. So it's really the process now going from A to C that I'm interested in. One of these at constant volume, one at constant pressure. And between those two kinds of processes you can characterize quite a broad range of behavior. When we want to specialize to an adiabatic process, then we're going to require that the net heat addition be 0. So we'll set the delta Q2 equal to minus delta Q1. Meanwhile, we can also identify the amount of heat that's needed to raise the gas by dT1 would be the so-called specific heat at constant volume. Likewise, there's a relation with dq2, the second heat addition, to that temperature jump through the specific heat for constant pressure. Here's our adiabatic assumption that the two heat inputs add up to 0. Put those both in terms of their equivalent in terms of temperature change and these coefficients. Then you can solve for one temperature jump in terms of the other. That involves this ratio of specific heats with Cp over Cv. That's called gamma. And so we see that one of the temperatures is going to be the negative of the other if you're going to have zero net heat addition. And here's our definition of gamma. Let's now use the perfect gas law, which we will also impose. Either in process AB or in the second process BC, we're going to have the pressures have to equal rho RT. If we do a differential form of this, it'll give us some idea of the way things must change. So that operating on the left side with the differential operator D gives the D pressure, the dP. Operating on the right side, you'll have the gas constant to be a constant, but you'll get d rho RT and then rho R dt. We're going to apply this differential form of the perfect gas law to both the first and the second processes. In the first process, density is constant, so when I rewrite this differential perfect gas law, I can eliminate this first term here. That lets us write, if we simplify a bit here, let me say how I'm going to do this. I'm going to divide the left side by the left side of the perfect gas law and the right side by the right half of the perfect gas law. And I think you can see there's some nifty cancellation here. And you get dP over P is dt1 over T, when we're talking about that particular change. Okay, in the second process, something happens in a similar way. We go from the B to the C under constant pressure. This time it's actually the dP that drops out, and you do have change in rho and temperature. And the relevant temperature jump is dt2 this time. So this time we can divide both of these terms by rho RT. I'll just do it outside. And that will cancel the RT, give you d rho over rho, and over here you'll get dt2 by dt2 by T. And solve again for for the one here, which is d rho by rho. And that comes out to be dt2 by T. Now let's go back to our adiabatic condition, namely that the temperature jumps have to be related. I'll repeat that equation number 1 here. And then we're going to take the temperature jumps that we just found in equations 2 and 3, and we're going to substitute that into equation 1. Here's a temperature jump, here's a temperature jump. And when the signs cancel, and when you cancel the temperature that's common on both sides, you get this nice relation here. dP over P equals gamma d rho over rho. I'm going to treat this then as a process going from our point A all the way to our point C, in which we understand the differential nature. So I'll kind of smooth those two sub-processes into one, involving a total pressure jump and a total density jump. We then find that this is an integrable relation here along that path, and you come up with the logarithm of pressure equal to gamma logarithm of density, and then add in an integration constant that we'll put in logarithmic form as well. Now, by the rules of handling logarithms, this gamma can be brought inside as an exponent, And then when you have the sum of logarithms, that's the same as the product when they're put in the argument. We're now in the interesting position of having two logarithms equal each other. Therefore, the arguments must equal each other. And that is what gives us the adiabatic law here. We might want to think of this equation as eliminating density from the problem. Now we've got several very important concepts under our belt. We have the idea of the speed of sound of a small disturbance. We have the adiabatic law. And so we have some one-dimensional ideas that we've done in using differential arguments along a path, along one-dimensional flow disturbances, and so on. Those one-dimensional arguments are pretty useful. I'm going to continue that in our search for the three-dimensional Helmholtz equation. So we'll continue our discussion with a one-dimensional discussion of the dynamic laws for acoustic motion. I'm going to have to do both conservation of mass and the momentum law in one dimension. Then we'll show how to generalize that into three dimensions. The conservation of mass now would be for a flow in this small tube considered to be one-dimensional in the sense that they're uniform properties along the cross-section here. But things are changing along the length of the tube. And this can be an unsteady process. The basic conservation of mass idea is that if you find the time rate of flow into this control volume. Now this is a stationary control volume, fluid's passing through it. And so this is a mass flow in, this is a mass flow out. And it's done in a differential way. This is really like a Taylor expansion where you take the reference value at the left face and then add these incremental quantities. But if the flow on the left into this volume exceeds the flow out, then you're going to have an increase in the total material in the box. And that's what has to be accounted for. In order to calculate the material in the control volume, we need a density at the center, and that's why I have expanded at the this equation level here. That's our density, and it's evaluated at a half of the small distance from side to side on this box. So our small distance is dx. And we're evaluating density at dx over 2, and that's a small change from the left side. Now the conservation of mass law then is that the flow in on the left minus the flow out on the right has to equal the time rate of change of the material in the volume. There's a uniform area A throughout, and then that cancels, shown by these blue lines. As often happens, you get a cancellation of the dominant term. You might call it the zero order term, the rho v on this side, as well as, which was a total inflow, and then minus the outflow that matches. So you're left with these differential quantities. So we're going to end up with a relevant equation then by balancing off the terms. It'll be this group of terms and this one here basically, including the dx at the end. We'll carry some of those terms into this next figure. Here on the left side I show a first order term, and that was a spatial derivative on this rho v term. On the right side there's a first order term with a time rate of change of density, and then I've carried a second order term just for good measure, and then we throw it away immediately because it's of size dx squared. So we'll just set that to be 0. With the equation holding over an arbitrary dx distance, we'll let that shrink down to the reference point x0. We'll cancel the dx. Then we'll note that the x0 really was an arbitrary point along the x-axis, so we view the result as a differential equation that holds at any point along that axis. So that's our continuity equation in one dimension. Let's follow up now with the momentum equation. Here we're going to take the cumulative impulse from all the forces that act in the x direction and set it equal to the change in momentum in the x direction. This is done over some reference delta t that's common to all the processes, and we just cancel that out. It's an arbitrary time slice. Many people in fluid mechanics are familiar with that equation to the extent that they just write down the summation of forces to be the rate of change of momentum shown here. So if you've had some experience, you'd rather start at that point, I would guess. The forces then tend to be these pressures times areas, and you'll have the pressure on the left face pointing to the right. We subtract off the pressure on the right that's aimed to the left in the minus x direction. As often, you get a cancellation of the dominant terms. Then the change of momentum would be the time rate of change of some average value of momentum if I just take it at the center of that box with the rho v, and then it will turn out that the higher order term here can be neglected. You've got a dx squared term, whereas these over here, this one over here is only dx. So we'll also neglect that term with the red arrow as being small. As before, this is really an arbitrary point x0 along the x-axis, and we'll treat this as a differential equation valid along the x-axis. So now you have the pressure gradient, which is causing a time rate of change of momentum. We now have a one-dimensional conservation of mass and a one-dimensional momentum equation. Let's try to drive a wave equation in one dimension using those. Basically, you have this x-axis representing the domain of our problem and some kind of a pressure field shown as the red wavy line. Now, the pressure is going to vary somewhat from the ambient or the reference value P0, and we'll call the variation P prime of x and t. These are functions of x and time, so it's definitely unsteady. Density will likewise change. Velocity will likewise change, and temperature, although it's a hidden variable at this time, would also change. We're going to only deal with still air, so in a minute I'm going to drop out the V0 term. I'd love to do otherwise, but we know that we don't want to get into aeroacoustics quite yet in this entire lecture series. In fact, there are many problems where that would be fun to do, but it's fun to just track that term for a couple equations and see how it goes. If we put the perturbed values into the continuity and momentum equations, we get these two laws. Now, we're going to expand those and see what the relevant terms are. What you're asking for is to define the state of this system at some point, like this point, in terms of the perturbed pressures, densities, and velocities. And those must coordinate in a way to satisfy these laws of physics. So you can't just have arbitrary perturbations here. They are linked together by all of the equations that we have discussed. In fact, 6 in number. If we included temperature here, there would be the 6 field variables and the 6 equations. Now, in our one-dimensional problem, we'll limit this to what are really 4 equations in 4 variables. So the counting is a little different for one dimension, but still valid. Now, the continuity equation has all these terms. We're going to drop this one in a minute and this one in a minute on momentum. But the idea now will be to see the relation and to see what of these higher order terms do we have to carry. Very often there will be a cancellation of the what we might call the zero order solution, and you'll see that happen again. Let's expand the continuity equation first. We'll consider the fluid to be still and drop out the V0 so that we're only left with the perturbed velocity. There's a derivative attacking these terms, but the derivative doesn't change the relative size of these terms. We see that the rho prime v prime is a higher order quantity. That's going to drop out. I do carry that along and with the derivative of each of those in turn, but then the red arrow means I'm canceling those out to be close to zero. What does survive is this derivative on x of rho 0 is a constant, but the v prime is not. So you get rho 0 dv prime dx. So that's a first order term. Over here is a first order term, d rho prime dt. And so now we're left with, indeed, these two terms that make up the expansion of the continuity equation. And that is valid, and we can drop those higher order terms precisely because of the very small perturbations that we encounter. I'll repeat again that our perturbed values may be 1,000th less than the baseline values or the reference 0 values. The momentum equation is likewise expanded, and we have the pressure, density, and velocity expansions. These derivatives don't affect the pressures. That'll drop out. You see this term here is just going to die. And we're going to be left with dp prime dx right here. Then there are higher order terms here that I've carried. The derivative won't matter. And so the surviving term is going to be d by dt of rho 0 v prime. Rho 0 is a constant, comes out front. dv prime dt. So this becomes our momentum equation that I'll repeat in the next figure. So now we have the momentum equation shown here, and that shows the pressure gradient here that tends to accelerate the flow. Now what we'd like to do is combine the continuity and the momentum equations, which are first order partial differential equations, and then we'd like to combine those into one single second order partial differential equation, hopefully involving only one variable. That's going to be tough. What we'll do is use differentiation, which is a common trick on this. And if you go back in your study guide and look at the conservation of mass equation, you'll see that there's a term that has a rho 0 on it. Let's try to get rid of that term and the one here with the rho 0 in the momentum equation. And we do it by taking a derivative in time on the continuity equation, and then we do a derivative on space in this momentum equation. That leads us to these cross derivatives on the x in time on the term that has the rho 0, and what do you know? Those are equal. So what if we now subtract the top equation from the bottom, and you get a second derivative on p prime by x squared, and then minus second derivative on rho prime by time squared. So it's still a partial differential equation. It's second order. Unfortunately, it still has two variables in it, and we'd really like to get that down to one. So we'll apply the adiabatic law now. Let's write down the adiabatic law relating density and pressure. We earlier worked on that at length and found that the speed of sound dp d rho was gamma p over rho, and you get that just by differentiating the top equation. An interesting thing that occurs then is that we need derivatives like d rho dt, and we can do that through a chain rule of d rho dp, which is a total relation, and then dp dt. But d rho dp we know to be 1 over the speed of sound squared. That leaves us converting our density variable into a pressure variable, but with the speed of sound associated. Now, a second time derivative is just done directly because the speed of sound doesn't vary with time, and so the derivative attacks both sides in the same way. And that lets us, on the term on the right side of that second order partial differential equation lets us convert it into a pressure relation. And look what we've got now. Second derivative on space on P prime, second derivative on time on P prime. This is called the one-dimensional wave equation. We now have a second order partial differential equation, which is a field equation. And this would be true for all sorts of pressure perturbations, not just sine waves in space and time, but other kinds as well. Our wave equation is valid for pressure disturbances that are not necessarily harmonic in space or time, so it's valid for general pressure disturbances. One thing that's to do just as a short exercise before we go into 3 dimensions is to look at a traveling wave, and it could be any spatial dependency you would like, square wave, triangular wave, or whatever. We're going to assume that, just postulate that there is something, let's say it's a triangular wave in pressure with space. So this is pressure versus x, and that this is going to be moving at some speed, let's call it a. Suppose we don't know that it's going to have to move at the speed of sound, and we're going to try to see if we can snocker this wave equation and get it to accept some other wave speed. So with that form, f is meant to be a general function of this argument, such as that triangular wave. Now that wave is moving, since it's x minus at, it will turn out that's a right moving wave with speed a. Speed a. All right. So we put that into the wave equation. You put it in on the left side, 2 derivatives on x. They're going to just cough out the derivatives on the argument without any change, and we can call that derivative of the total quantity with a prime, so you just get f double prime. On the right side here, you're going to get 2 time derivatives. They're going to cough out the minus a factor and then relate to the prime or the total derivative there. So you get the minus a squared out front. And if you then cancel the common waveform here, or better yet, factor it out front, I guess, at, then you're going to have here 1 minus a squared over c squared, that quantity to be 0. Now, since this is an arbitrary waveform, although we're imagining a triangular wave, the only way this will happen will be if c equals a. Really, conversely, hopefully, the wave speed a that we've proposed is going to have to be set equal to c in order for this to be a meaningful solution. So we've just proven that really an arbitrary traveling wave has to propagate at the speed c. And it's this location in the differential equation that requires that. That's where the physics is caught, and people look for that position then to be the wave speed of the equation. It's built right into the equation in this linear form of acoustics. Let's now extend our work into 3 dimensions. The time derivatives don't change their sense. They're derivatives in time at what goes on at a point, and that's no problem. But the space derivatives do matter. What were once derivatives on x now have to become gradients, and what were once second derivatives now will become Laplace operators. So to extend the wave equation into 3D, we need here, where the second derivatives on space are involved, to have the Laplacian. It's this inverted delta, some people call it a nabla del, and it's on the pressure. Now previously we had carried primes on this, but now we're going to drop the primes. That's a convention that people in acoustics follow. So I won't try to rewrite history here. So we don't have the primes anymore on our pressure perturbations. That's because everybody knows what the game is, that the only pressures of relevance are these perturbed pressures. The term that has a time derivative is unchanged, and so then this becomes the 3-dimensional wave equation. The Laplacian itself is sort of an averaging operator. It's an interesting thing. When we get into equations that don't have time quantities on them, then it tends to give you elliptic operators that are nice, smooth operators. Currently, though, we do have what would you call a hyperbolic differential equation as long as the time derivatives are in here. Okay, so c is our propagation speed, so-called speed of sound. P is really what we used to call P prime. A very special case in acoustics is that of the harmonic wave, both in space and time. This is a kind of sound impulse put out by a loudspeaker giving a pure tone, let's say. We know that actual sound waves are combinations of various frequencies, but if we can handle a single such frequency at a time, then we can generally solve the problem. Some people call this solving the problem in the frequency domain, and it means that you do concentrate on specific frequencies and then superpose. The superposition is valid because of linearity. Now, if we're going to do that, one way to do it is do separation of variables on space and time. Here we have our original pressure perturbation over here. We've dropped the prime on it. It's a spatial perturbation and then a complex exponential in time. If you want to get the effect of a traveling wave, you can use a complex spatial distribution here. I'm using, temporarily at least, this tilde over the spatial part of the pressure because it's not really the same function as the one over here. An interesting thing then is, if you look at the second derivative of pressure, because you've got the exponential time behavior, the two derivatives cough out I omega squared. I is the imaginary number. When you square it, you get -1, which shows here. The frequency is squared, and then you have a quantity here, which really is the original pressure. So you get that the second derivative of this field variable is minus omega squared times the field variable itself. When we put this into the wave equation, remember there was a location here, and it actually is where these terms are. We are then bringing in the frequency squared and the spatial part of the pressure distribution. There's also the minus change. This minus sign comes in and changes the sign from what was once minus. And so the wave equation has become the so-called Helmholtz equation in honor of one of the big names in acoustics. Might have called it the Rayleigh equation, but there's already a bunch of those. This is our equation. Now another trick is in acoustics that in the textbooks and the manuals and so on, people tend to drop the tilde at this point. And so you have to be aware that the time part of this equation has been extracted and simplified and appears only now in the frequency. So this is a frequency domain equation that's valid at a certain frequency, omega. Another tidying up that's done is to use omega over c and call it the wave number, k. And that is done here. And so you end up with a very simple equation, but it's got a lot of insight and intuition built in. First of all, that this is really a perturbed spatial distribution of pressure, and then that this wave number has the frequency built into it that gives you something about the dominant excitation in the problem. It's got the speed of sound built into it, which tells you something about the medium. Now, this Helmholtz equation has to have boundary conditions to choose among all the different possible pressure fields that might satisfy the field equation. And as we've mentioned before, you do that through combinations of giving surface velocities, surface pressures, and then some combinations of impedance and velocities. I have another figure on that coming up next. I think now you see it's appropriate to have boundary conditions that occur on pressure and derivatives of pressure, because that's what our field equation now has. I've discussed these earlier, but the most important boundary condition really is the velocity boundary condition, and that's taken to be the default in problems where if there's zero velocity condition, that's like a hard wall, you get a perfect reflection off of that. Also, many times, not only do you have that passive type of boundary condition that's so dominant, but you also have active velocity specified when you have a relatively heavy body like an automobile engine. And suppose you know the motion on the surface of the engine, then you can solve an uncoupled problem where you just presume the air isn't going to change the engine's vibrations very much, and only the converse is true, that the vibration of the engine affects the air, and then you use those surface velocities as the input to the acoustic program. So velocity, both passive and active boundary conditions, are really important. Pressure is probably used less often. You might think it would be used more, but it really isn't. If there's sometimes pressure release, if you have an intersection, say, between water and air, where the pressure in the water will be presumed to go to zero at that boundary, that's one possibility. You might think there might be a pressure condition when you have an opening on a closed body. For instance, there is something called a Helmholtz resonator where you have a dominant cavity effect, but there's some opening to the outside world. You might think, well, you'd set pressure equal to ambient pressure out there. Well, more often that's done as an impedance match, and then even then there's some question where you do that. So I think the impedance is probably the second most important boundary condition, and often it's on a surface that has some acoustic treatment, and therefore an incoming pressure wave is modified to some extent. Some of the energy is absorbed, it's not all reflected, and then that's usually given in the term of an equation with a complex acoustic impedance Z. And so the pressure and the velocity are linearly related, and these are done in complex arithmetic. Lastly, if you have something like the padded surface of an automobile ceiling, then you get possibly a case where the experimentalists know what the velocity of that roof of the car is, but yet it's a moving surface with some acoustic treatment. And that's why it's important to be able to do a simultaneous velocity and impedance condition, and those are blended together. Commercial packages for numerical acoustics have several capabilities. Some of them include finite element acoustic solutions, some include boundary element solutions. Most of the conventional general purpose structural finite element programs now have added acoustics and can handle the finite element formulation. That's known to be helpful in cavity problems, and there's a lot of work in the automotive industry being done with conventional structural codes that are modified. But the modern trend is toward boundary elements because of a saving in manpower on the meshing. You can have either the direct method or the indirect method, and we'll have lectures on each of these. The direct method, generally speaking, is a one-sided type of element in which you have the acoustic field sensed only on that side. The indirect method involves the acoustic field on both sides of a panel and works in terms of the jump on either side. As generally formulated, the finite element method would have many more equations involved because you have to fill a volume with elements. However, those matrices involved would be banded and symmetric. So you have the good news and the bad news. The direct method here might have either symmetric or unsymmetric matrices. The matrices will be smaller in that they have fewer degrees of freedom, but unfortunately will be filled, or that is typically fully populated. The indirect method can be made to become symmetric in form, and that's a help making the solution simpler. So let's have a showdown between finite elements and boundary elements. There are three main differences. In the finite element method, the entire domain must be discretized. Now, there is something called an infinite element or a wave element that's been developed in finite elements. These are not widely used yet. There's some approximation involved, but there is a way to get around this and to do exterior fields, although a little complicated at present. But generally speaking, finite element analysis fills the volume with elements. Boundary element methods, you only need to do the two-dimensional surface that bounds your problem. And the difference in those two is often a manpower difference rather than machine related, because it's easier to develop surface models. It's much easier to work in 2 dimensions than 3. The next point does have to do with exterior problems. Currently in practice today, it's common practice to only do interior acoustic problems with finite elements. But boundary elements are used both for interior and radiation problems, exterior problems. The research in the future might change this, because there are some infinite elements and so-called wave elements that are meant to extend from a finite body out to infinity. So there's some promise there. There's some very good researchers working in that area, and I don't know what the future will bring, but at present, just as an operating practice, I think you'd want to make that distinction. So, for instance, the automotive companies are using finite elements quite a bit for interior cavity problems for the inside of the automobile. The other thing, point 3 here, has to do with the symmetry and bandedness of equations, where finite element matrices, although being large, have both of those nice properties. But boundary element matrices are fully populated and possibly non-symmetric. So it's wise to pay attention to those things. They affect the solution cost. Fortunately, it is possible in boundary elements to do what's called zoning, and that does help and give sort of a bandedness to a problem which intrinsically has sets of equations that are fully coupled. It helps you break the solutions into disjoint sets of equations. In our problem session, I'm going to propose 3 different solutions for our wave equation and see if these are allowable pressure fields. Case A is a cosine in space and a sine in time, with a coefficient A out front, which would be an amplitude coefficient. This would often be used in a real form, and you might recognize then that this would be what's called a standing wave. It would have cosines in space that would change their sign sense, but tend to just oscillate back and forth then in this pattern, which is an envelope with fixed nodal points here. The second one is a general traveling wave. In this case, the shape of the wave in space could be arbitrary. The wave will be moving to the left with speed a. Thirdly, you could have this complex exponential form both in time and in space. Normally a person would interpret in most mechanics problems that it would be the real part of this pressure that would be of interest and would lead to real displacement fields in a structure. We'll see how this tracks through the wave equation. Let's look at our case A. This was the real standing wave. And if we substitute that into the wave equation, we recognize the second space derivative, the second time derivative, the minus sign, the c squared appearing. Remember, the c captures the material properties of the medium. So we're proposing a pressure disturbance with a cosine waveform and a sine time dependence. Now the cosine in the x direction survives these two derivatives, bringing out some constants, and then bringing the cosine term back again, and that is replicated on the other side where there is no space derivative. Likewise with the time function, there's no derivative on time on the left, so it survives, and on the right the two derivatives just cough out the minus omega squared, because two derivatives of sine omega t by t does that. You go through the cosine and then the minus sine again. You don't want this equation to hold true trivially just for some instant of time. Therefore, let's cancel the sine omega t, and you don't want it to hold just at one point in space. So, and we see it's in balance in that sense, both in time and space. So we'll cancel the space terms. You're then left with some constants here that must balance out in order to give us this 0 on the right side. And this is the expression that's obtained. Now, since the speed of sound is constant in a medium, an acoustic medium, this gives us a relation between the frequency and the wavelength. And so that's stated down here, that the wavelength is inversely related to the frequency. Now, of course you say, well, of course, but in my structural dynamics background, we were able to take a flexible wall and propose that the flexible wall move with any wavelength and any frequency. But notice what you've got here. This is an acoustic wave that characterizes the medium itself. And the springiness and the elasticity of the medium are caught up in the constant speed of sound. We're not able to maintain a pressure wave in air unless the frequency and the wavelength are related like this to the speed of sound. So in other words, to get a standing wave in this form, basically you have to resonate a cavity, is what it boils down to. You've got to get a reflection of waves off the two boundaries. We're going to go into this later, but it's a little bit different than in structural mechanics, than in vibration of bodies like sheet metal and so on, that you consider as affecting the fluid. This time the fluid itself is resonating, so it's got its own time constants built in. Now, you can also put this in frequency form in hertz rather than radians per second, and that's a trivial change where omega over 2 pi is set equal to the conventional frequency. Some people would rather have frequency in radian measure here, and so you can call it circular frequency or any other term, but often people would rather work with the frequency in hertz. Case B is the arbitrary traveling wave. We actually did this in the lecture as well, where we took this general traveling waveform. It's a wave traveling to the left, and when you do the two derivatives, you pick up the f double primes here and here. The amplitude can cancel on both sides, and then the arbitrary functional form can cancel on the two sides, and you get 1 minus a squared over c squared has to equal 0, or you must have your a equal c. So this will only work if you choose your pressure field to be moving at the speed of sound. Now, you can either go plus or minus. You can probably see here that A could either be plus or minus, and this will work out. So you can either have a left traveling or a right traveling wave. Case C was the complex form, and we'll again substitute that into the wave equation. The exponentials will retain their shape when they're differentiated. Everybody likes exponentials because when you take derivatives, they come back again, sort of like a cat with 9 lives, except exponentials have infinite lives under infinite attacks by derivatives. After taking the derivatives, there are some constants brought out, both on the space and time derivatives. But you again get a repeated functional form where the time terms can be canceled, the space term can be canceled, the amplitude can be canceled, and then you're left with these constants. Now, these constants have to be true, and if the wave equation is to be satisfied in some space, these have to hold throughout. We view the speed of sound as a known constant, so again we get a relation between the wavelength and the frequency of oscillation. So you can't get this kind of pattern of pressure except at certain relations between wavelength and frequency. This is due, of course, to the inherent springiness of the medium and what it requires. If there is to be a constant wave speed, then this has to be the relation. Finally, I do a short trick here to show the same thing, that if you view that complex exponential in a product form here where you sum the exponentials, then it looks like a general function of a traveling wave. In fact, knowing that we substituted such a general function as this one previously and found that the wave speed, where I've already put c here, had to hold, then we immediately see by analogy what the wave speed has to be, and that gives you directly then the relation between wavelength and frequency as we got before. That finishes our problem session, and so the following lectures will be on numerical acoustics.